Okay, so we have today the talk of Dirk Werner, that is a friend of the Institute, and he has been here a lot of times, I think, so he knows very well Valencia and the people from Valencia and so. And he's going to talk about the perfect theory of M-ideals, that in a sense sounds perfect, and I will see if this is the case or not in the following minutes. So thank you very much for coming again to Valencia, and let's enjoy the talk. Okay.
We enjoy it. Thank you for giving me the opportunity to speak here after 3 long years without any travels. It's good to be back on the road again. So, I was rethinking this talk in the morning, and I was thinking there's hardly anything new in the talk, but I hope you will still enjoy it. I will be playing with methods I've known for 20 plus years, and let's see whether I can get some mileage of it. So, this is not a typo, and although Centralblatt corrected this to the English word perfect, it is not meant to be the English word perfect, although it fits very well. So what are we talking about? M-ideals. What is an M-ideal? It's my love of 20, 30 years, but since we are in the 21st century, I decided I should ask the new wunderkind on the block, which is ChatGPT. And here's what they say. So if you think of it, you might say, it doesn't say anything. Indeed, it doesn't say anything. M-ideal is something where the dual is the dual or so. But let's go on. Here's the next mistake. M-ideals were not introduced by Johnson and Lindenstrauss, but they do have applications. That's fine. What else do they say? They say that L1 is an M-ideal. So this is wrong, as you will see in a minute, and also the whole question is wrong to begin with, because a space cannot be an M-ideal in itself, but it can only be an M-ideal within a bigger entity, as we will see when we study the real definition. So this was somewhat disappointing, and the disappointment will go on a little later. But first of all, the same question again, what is an M-ideal really? Hola. So, this is the first page of this seminal paper by Alfsen and Efros from '72, which is now more than 50 years old. And this is part of the abstract, and it has two parts. This is part 1, and I will now tell you what is really in there. But first of all, let us look at this definition that they give. So you have a Banach space and a certain subspace, which is called J for ideal. And they say this is an M-ideal. It's defined by duality. If in the dual space there is a so-called L projection, so it is additive, it's given here, and the kernel is the annihilator of J. So if this projection was actually weak-star continuous, if it was the adjoint of another projection, then this other projection would project onto J itself, in which case we would speak of an M summand, because it has a direct summand. But in general, this is not so, and this is the most important thing. In the abstract, Alfsen and Efros say this type of subspace is analogous to a two-sided ideal, and indeed an M-ideal in a general Banach space is the same as a two-sided ideal, a closed two-sided ideal in a C-star algebra. And this again is the same as a so-called split face in a compact convex set, which were the specialties of Alfsen at the time. So, examples are of course the zero sequences within the bounded sequences. So here, if you think of this in terms of continuous function spaces, then the generalization is you have a space of continuous functions on a compact set, and you have a subspace consisting of those functions that vanish on a certain portion, and you have an obvious projection that satisfies the L1 type condition by looking at the dual space, which is represented by measures. So, but here you can do all this more or less by hand without any reference to these representation theorems and the like. And the non-commutative version of this would be replacing zero sequences by compact operators, first on Hilbert space, and bounded sequences by bounded operators. And this is, if you take p equal to 2, this is one instance of a two-sided ideal. And again, in this very special example, this is a result due to Dixonier from the 50s already. And then after the Alphen-Efros paper appeared, there was work on studying those Banach spaces that have the same property as Hilbert space in this connection. And it was shown that the little LP spaces work, the capital LP spaces do not work. And the final answer was eventually given by Nigel Kelton. So here are the closed ideals. This is what they wanted to show. And here are all H spaces. So I'm not going into much detail here, but all H spaces come in two varieties. Either you say that this modular is less than 1 for some lambda, or finite for some lambda, or for all lambdas. Depending on which version you look at, you have the spaces denoted by h or by little l, and what you get is an M ideal. So finally, capital L1, what ChatGPT claimed to be a key example. So of course, the question should be, where is it going to be an M ideal? And of course, I can take this space and make a direct sum with any old other space, and then I have an M ideal if I take the supernorm. But this is not fair. So you want some reasonable superspace where you have an M ideal but not a direct summand, and one can prove that this is impossible. Peter Hamann proved this, for instance. So let's go back to ChatGPT and let's ask them, what do you know about Alphen-Efros? What did they do? So surprisingly, they know something. They know the first names, Erik Alphen, Edward Efros. That's absolutely correct. They do not always know first names correctly or initials correctly. Anyway, you may not want to read all this, but again, it's a very verbose description of basically nothing. And I would also like to draw your attention just to this final sentence here. The work is considered important in the study of M ideals and influence many subsequent developments in the fields, because you will read the very same sentence in a minute or two.
May I interrupt you? I'm sorry.
Sure.
So an M ideal depends on the subplot space.
Yes.
It's not intrinsic. It depends on
Yes.
where do you sit.
Yes, it's like an ideal in an algebra.
Yeah. So there is no internal characterization of ideals because I mean, not looking at the dual, but because it depends on the subplot space.
So yeah. So there's one situation that I will come to in a minute, which is sort of canonical, where the superspace is sort of natural, and I will maybe come back to
So
your
something
questions.
can be an M ideal here and not an M ideal there.
Yes, indeed, yes.
Sorry for the interruption.
No problem at all. So here's the situation, probably addresses Vicente's question. If you have a Banach space, then there's a canonical superspace named the bidual. And you might wish to study, is it an M ideal or not? And in this sense, you do not need to mention the bidual of the superspace explicitly once you understand that you're studying this embedding. Right. So this was the subject of Peter Hamann's dissertation, and he called them M-embedded spaces. Actually, he also had another shorthand version for this called MM spaces. Then he went to Oldenburg, and Klaus Floyd clearly did not approve of this abbreviation because it doesn't explain what it abbreviates. But we were still using this for many years in sort of private conversations. And also there's the dual case of L-embedded spaces, the LM spaces, that I'm not going to talk about today. So, on the previous slide there were some examples, and those here is the list of those that are M-embedded. So there are natural spaces in this class of spaces. And concerning the order spaces, I have to mention that you need some version of the delta 2 condition for this to work, but I'm not going into that. Then one other thing one has to keep in mind is a reflexive space is very trivially M-embedded because the bigger space is the same space. So the projection we were looking for is just the zero projection or the identity projection. And so these spaces allow for a rich theory with many natural properties stemming solely from this special geometric embedding. And here is a list of some of these properties. So first and foremost, they all contain copies of C0. And the dual is separable when the space is separable. More generally, the dual has theorem P. There are these Lipschitz properties. And when moving to non-separable spaces, it's a theorem of Gilles Godefroy and Marianne Fabian that these spaces are weakly compactly generated. So as I said, these properties mostly come from work by Peter Hamann together with Oswald Niemann, and also work by Gilles Godefroy in the 80s and 90s. So here's another question to ChatGPT: what did Peter Hamann do? And now things really get surprising, because ChatGPT makes a connection to Lipschitz free spaces that Peter has never looked at as far as I know. And the theorem that they mention, the Lipschitz free space over an M-ideal, is again an M-ideal. I don't even know what that means. To me it's complete nonsense. So this little digression tells me that ChatGPT for mathematics or for high-level mathematics is pretty much the same as these math-gen programs that write nonsense papers that look like real sentences but do not carry any meaning. And when I read that economists have used the program to write research papers, then I'm very worried about their research, I must say. So in mathematics, probably we're going to be safe for a year or two before the program catches up and does much better work than today. But for now, we have to do the work ourselves. So, remember that the definition of an M-ideal was given in terms of a projection in the dual space. So if you have a space and a subspace, and you want to study whether this subspace is an M-ideal, you need to have access to the dual space of the superspace, which might be not so easy if you think of compact operators and the bounded operators. There's no obvious way to represent the dual space of the bounded operators in the same way as in a basic functional analysis course, you show how to represent the dual space of little LP. So the first part of the Altsneffers paper then provided an alternative that does not mention the dual space. So this is the so-called three-ball property that I will show next. So the main result of the first part of their paper is a subspace is an M-ideal if and only if for each n something happens, if and only if for three balls something happens, and they have these figures that I will now walk you through. So the condition for three balls is the following. You are given three open balls, look at the right figure, such that each of them meets the subspace, like here, here, and here. They have a non-trivial intersection, which is the shaded area. And then the requirement is that the intersection also meets the subspace, which is this bit here. So this figure shows the maximum norm in R2 and gives a convincing argument that these balls satisfy this intersection pattern. The figure on the left shows already with two balls, this fails for the Euclidean norm. So on the left you have two balls that intersect non-trivially. Each of them intersects the horizontal line, but there's nothing in the intersection that is also in the horizontal line. So for the Euclidean norm, already the two-ball property fails, but for the maximum norm, three-ball property appears to work. And their theorem is this is characteristic of M-ideals. A closed subspace is an M-ideal if and only if for any three balls like this, I have this intersection pattern. So what about n equal to 2? They also have a counterexample in the real case to show that two balls are not enough. And where does all this enter in the proof? So basically you need an intersection condition with two balls to cook up a projection in the dual space that is additive. But you need the third ball to prove that it is linear. So with two balls you get a nonlinear projection, with three balls you get a linear projection. This is the catch in all this. So here I'm talking about real Banach spaces, and the corresponding question for complex Banach spaces turned out to be much more involved. It was only in the 90s that Erhard Behrens could show that there's also a counterexample like this one in the complex case. So now there's a version of the three-ball property that is very suitable for computations. It was worked out by Oswald Lima, and it is this. So what are we having here? We have an inequality, or more precisely, three inequalities. So a subspace is an M-ideal if and only if this set of inequalities is satisfied for some y. And this is a special case of the three-ball property with the centers in a special position. So first of all, we have three open balls of the same radius, 1 plus epsilon. Then the centers are x plus yj, where x is in the unit ball of the superspace and the others are in the unit ball of the subspace. Okay, then each of them intersects the subspace because yj itself is an element of this ball. They also have a point in common, namely the point x. And the requirement here is they have to have a point in common that comes from the subspace. This is this y. Okay. So now in terms of computation, it doesn't really make much of a difference whether you have 1, 2, 3, 5 or 7 balls. It's technically always the same type of computation. And we will have a look at one such computation in a minute. Let us suppose we want to show, using this criterion, that C0 is an M-ideal in L infinity. So let's try. What do we have to verify? Given these data, we have to find some y satisfying these inequalities. Now I will try to explain by drawing something, and I will actually only draw one yj, because otherwise you won't see much anyway. So we are given one point in the unit ball of L infinity, so which is this one. And you are given 3 points in the unit ball of the 0 sequences, of which I will draw now only one. So being in the 0 sequence means at some point it's going to be smaller than epsilon. So now we want to find this y. And we just want to use the fact that the ball here is pointwise dense in the ball here. So if we want to use stronger methods, then it's easier, but I would like to show you how to do this only using this density, because it will come up later again. So, how to do this? Well, we will first devise an element in C0 that coincides with a given x along a stretch of natural numbers, and this is determined in such a way that our other sequences are smaller beyond this index. So we can find a 0 sequence by density that is essentially the same as here and will eventually also be small. But we don't really have a good control of what it does in between. So it's like this. And now if this is our candidate for y, then what do we get? X minus y plus yj, x minus y. So this is more or less 0 because it reproduces this. So it's essentially the norm of this bit. Fine, less than 1 plus epsilon. And beyond this point, the sequence x has norm 1, all the others have norm epsilon. Again, this is small. So this is 1 plus epsilon, but what does it do in the middle? This is something we can't control so well. So here, these bits are epsilon, but these might interact to get a norm of size 2. So let's continue simply and do the same trick again. So we now, in the second step, find a sequence that again reproduces our sequence x, then does something, and then it is small, and so on. And now, the trick to find this y that we are actually using is to average all these things. Because then if you average them, so each of them only has one block where there's a problem in the estimate, and if you average them, then this block, in this block, the norm will be epsilon. So if this is 2, and you do it 10 times, then the average will have norm 0.2. So this is basically the construction one can do at this point to show that the 0 sequences are an M-ideal given this method. So, but let's go on. So, here's Carl Michael Perfekt. He's a Swedish or Norwegian mathematician, I'm not sure. He had a PhD from Lund University in Sweden, but he now has a position in Trondheim in Norway. And in between he was in the United Kingdom. So, what he did is he more or less accidentally found a big number of spaces together with a canonical superspace that are in biduality and for which even the M-ideal property is true. And the situation is, in very rough terms, you have a big space E where the norm satisfies a capital O condition, like the sup norm here, which is bounded, so it's capital O. And you have a subspace E naught, like the zero sequences, where the same condition is given in terms of the little o condition. So here sequences are bounded, capital O, here they tend to zero, little o. And this is the hallmark of the situation, of which there are many more examples, like the famous BMO space, with its subspace of vanishing mean oscillation. Here, this is a pair of analytic functions with some weight. So E is supposed to mean all the analytic functions in the unit disk that remain bounded when multiplied by a certain weight phi. And E naught is the subspace of those functions where the limit when the variable tends to the boundary goes to zero. Right. So for this last pair, I proved many years ago that this is a pair in M-ideal position. And this is one of the situations here. And finally, sorry, the Lipschitz spaces, about which I'm going to say more in a couple of minutes. So it's actually, since the alpha appeared, it's the Hölder space. It's, instead of the Lipschitz norm, we look at the Hölder norm. And I will explain in detail what these spaces are when we come to that point. So all these examples are examples where you have canonical biduality and also the M-ideal property. And Carl Michael Perfekt wrote a couple of papers in which he set up a scenario which generically yields spaces in biduality with the M-ideal property, and he shows how to apply this in these situations, or some of these situations. So what I did is I tried to expand his ideas a little, because his assumptions are sometimes unnecessarily restrictive, because he wants to use certain results from measure theory that require, for instance, that some space is metrizable or so, that you can get around simply. So, how does he do this? We are now trying to explain this construction from the wrong end, as it were. And you will see in a minute. So, again, we want to describe these E and E naught things, but for this we need auxiliary spaces, a reflexive space X and an arbitrary space Y. Then we look at the operators from X into Y, and we select a subset script L of this operator space that is equipped with a locally compact Hausdorff topology, which is finer than the strong operator topology. So, In most cases, y will simply be the real line. In which case, I'm talking about operators from x to the real line, that is functionals. And this set script L, consisting of functionals, is equipped with a topology finer than the Wigstar topology, point-wise topology. Right, so this is given, and now the space E is defined to be those vectors in X, so it's by definition algebraically a subspace of this X, for which this soup is finite. Right. You apply all these operators in script L to X, and you get a family of vectors in Y, and the requirement is this is finite. And then E naught, the same thing with a limit condition. So here limit t to infinity means L is a locally compact space, so there's the Alexander of compactification, and this is, as it were, the point infinity. So, in words, it means Tx gets as small as you wish of a compact subset of L. This is what it is. And to go on, well, this set L has to be rich enough to make any conclusions, and one consequence of this richness would be that the norm, as indicated there, is actually a norm and not a semi-norm, and the whole thing is complete. But then E is automatically and continuously embedded into X. Now in practice, you will work the other way around. You are given E and E naught, and to put it in this framework, you have to find X, Y, and L so that E has exactly this representation. So you are already given a Banach space, and like that one, and we'll see in a minute how we can arrange C naught and L infinity in this framework. Now here again is a richness assumption of this. I mean, the ball of the smaller space is dense in the bigger space with respect to the norm of X, right? So all these elements are by definition in the space X, and the density is described in terms of the norm of the space X. So now let's try to represent this pair C naught and infinity in this framework. And one way to do it is look at the weighted L2 space X with weights 2 to the minus n. Y is the real line. As I said, this is quite often the proper choice. And the subset of functionals is just the evaluation functionals on this Hilbert space. The topology is going to be the discrete topology, finer than everything, so all is met. And now, what are the vectors in X for which the sup En star of X is going to be finite? These are precisely the bounded sequences. And what are those for which the limit n to infinity tends to 0? These are precisely the 0 sequences. So we have shown that this pair, L infinity and C0, matches the general description and also the condition A, the density condition. So here is what you can prove about a situation like this. Under condition A, then E is always canonically isometrically isomorphic to E naught. Same way as L infinity is a bidual of C naught. It's always the case. And also you get the M-ideal condition. So this is a little bit roundabout in Perfekt's papers, and my aim was to find a more straightforward proof of this building on this three-ball intersection pattern. So in order to prove these theorems, I found it advisable to look at the embedding of E to the continuous functions as given here. And then the crucial property that one can use is that you have a module. So you can multiply a vector valued function like that by a scalar function, a module property of the space. And likewise with the mod. And this replaces Perfekt's argument where he uses the theorem due to Ivan Singer, which describes the dual space of the continuous function space, the terminal vector measures. So if you do this, then the condition A translates into more traditional terms, uniform convergence on compact subsets. And again, to get theorem 2 about the M ideals, this is custom made for the three-ball property. Again, the module property helps a lot. And what you try to do is you repeat this procedure from this classical case. So needless to say, this is a little more technical than the simple idea that I tried to outline, but eventually it works. So here's a little warning. Essentially, this works for separable spaces, and for separable spaces only. So the first non-trivial candidate for a non-separable space to be squeezed into this framework would be the C0 space on an uncountable set. But one could prove that there's no injection whatsoever of the C0 space into any old reflexive space. So for this type of non-separable space, this approach will not work. Right. Now finally, let's come to Lipschitz spaces. In this slide I showed a couple of minutes ago, there was already mention of the Hölder spaces for the classical unit interval. And this embeds, as it were, into the general theory of Lipschitz spaces in the following way. So you're given a metric space in which one point is distinguished. So if your metric space happens to be Banach space, you will more often than not pick the origin, which is why this distinguished point is often called zero, also when there's no algebraic zero in the space. Right, then you look at the Lipschitz functions that vanish at the distinguished point and equip this set with the Lipschitz constant. This was fast. So the Lipschitz constant is going to be the norm on the set, and since we require all the Lipschitz functions to vanish at P, we really get a norm and not only a symbol. So this is the big Lipsch space, and the small one is the one where these difference quotients simply tend to zero uniformly in X and T. So this is a well-defined definition, but of course it might simply give you the zero space. So if indeed the metric space is the unit interval with the Euclidean metric, then what you're asking here is that you have a function whose derivative is zero. So this is going to be a constant function. The constant function vanishing at some point has to be the zero function. So in the classical Euclidean norm on the unit interval, you really only have the zero space here. Also, it should be noticed that the choice of the distinguished point doesn't play any role. So if I pick some P, Alfred picks some Q, and we both build our spaces, then they are naturally isometrically isomorphic. So again, if one wants to study this situation in the framework of perfect construction, one has to have some richness assumption, which in this case reads that the small Lipschitz space is the ball of the small Lipschitz space is pointwise dense in the ball of the big Lipschitz space. So this rules out, of course, situations like this one. And also, I'm only looking at compact metric spaces at this stage. So now, given this assumption B about compact metric spaces, you can prove the M-ideal property and you can prove the biduality property using the ideas suggested by Perfekt. So what he did in his paper, he only looked at subspaces of the Euclidean n-space, compact subset of Rn. And to make his procedure work, he had to use this reflexive space X, which for him was a complicated Biasov space. And he asked in this paper, can one do it for general metric spaces? And indeed one can, as I have proved. And the metrics and the space X, the Euclidean space X, is again a weighted Hilbert space, a weighted L2 space. So much simpler than a Biasov space.
One little question. You don't assume any uniformity in this limit to the tending zero?
In this limit?
Yeah.
Yes, it's uniform in essence.
Uniformness.
So what I said about the derivative would not need the uniformness. It
Yeah.
would just
Yeah,
simply, even if it's pointwise,
Yeah.
it would show that it is zero. But this is a stronger condition.
Yes, of course.
So the person who was first to study all these things is Nick Weaver, who has written this book that is often quoted about Lipschitz algebras. And he was the first to prove that under these conditions you always get a biduality here. And in his results, one can also study certain non-compact spaces that are beyond this approach. He probably didn't know about M-ideals because he doesn't treat them. And if he did, he probably also have studied the M-ideal property. So one person who did study the M-ideal property is Nigel Kelton. And what Nigel proved was that under all circumstances, this small Lip space is always an M-ideal in its bidual. But the bidual need not be the big Lip space. So for instance here, it's very true that this is an M-ideal in its bidual, but it's a trivial statement. But of course there might be situations in between the very trivial reduction to zero and this density condition. Yeah, and the way he did it, he proved that one can embed such a Lipschitz space into C0. Not totally isometrically, but as well as one wants. And this is good enough so that this M-embeddedness will be inherited from C0. Now, if you have a metric D, then you can study the associated Hölder matrices D to the alpha. So this is sometimes called the snowflaked version of the metric, for reasons I do not completely understand. But this term appears in the literature. So what happens is you have a metric D, and you do all this replacing D by D to the power alpha, like root D or so. Alpha is between 0 and 1. And you have a new metric, same topology, but a new metric. And in this new metric, these quotients, of course, look different. And again, returning to the unit interval, for the Hölder metric, there are non-trivial functions satisfying the little lip condition. And all classical Lipschitz functions do this. So what I proved is, if you go to the snowflake version, the sleep alpha spaces, then this density condition is always satisfied. Therefore, we get all the results about the alpha Hölder spaces. They are biduality and they are ambiguous. Right. So I believe this is all I wanted to tell you. And let me think if there's anything I still had in mind that I would like to add at this point. Maybe not for the moment. Thank you.
So thank you very much for the talk. Maybe there's some questions or comments or whatever. I'm almost make some comment. Fred.
Well, one is a spoiler about ChatGPT. Maybe you don't know, this very recently, the version that appeared by the end of last year, it's only fed with the data until 2021, but now they offer the possibility with Chrome to have a plugin so that it goes directly and asks internet. And now things that you don't have before in this, you get even references and so on. So maybe this kind of questions that you were putting, if you use this possibility with this plugin of ChatGPT to Chrome, then you get different responses. So these are
That might be the case, yes.
That might be the case.
Yes.
So maybe you don't have to wait for 2 years or half a year for that.
But these conversations that I showed you, I think the problem was not that they didn't know last year's data.
Exactly. Yeah. It's a question that it's working differently. But now with this version, combining with the internet searching, it's different. On the other hand, you lose the dialogue possibility because you were continuing as referring to things before, and then it remembers ChatGPT, but now no. So you pay this price in a sense.
Yes. So before I come to your question, Pilar, let me just add a little anecdote here. I also asked lots of other things just for my pleasure, and one thing they get completely wrong all the time is, I studied the Daugaved property, so I asked about Daugaved, and ChatGPT said that his initials are what are they, like V.E. like Vladimir Ilyich, like Lenin's initials. So the correct initials are Igor Karlovich, so E.K. So this is a little surprising because it's very easy to find this out. The name Daugaved is not so widespread that there are very many persons having this name in mathematics. So it did get right what the Daugaved property is. It did get half of the examples right, 50% hit. And then there was another thing. It's like talking to a liar.
Of course.
So I asked something and ChatGPT said, there's a paper called Daugaved Property and Convexity by E. Cascales and J. Orejuela. And it has appeared in this and this journal, this and this volume, these and these pages. So I was very surprised, because I've never heard of this paper. And of course, Bernardo Cascales was not E. Cascales. Anyway, I checked Centralblatt for this reference, and maybe sometimes you overlook something, but you see there is no paper from page X to page Y in the journal. It was completely made up. And then when I wanted to complain, the connection broke down. Finally. So.
The other thing was a mathematical question. It was about, maybe I missed something about not the second proof of with the perfect theory of C0 being an M ideal in an infinity, but the first proof with this 4 condition that you have in the theorem after, I mean, this 3 ball.
Yes.
Okay.
Yeah.
I mean, you have this inequality that had to be satisfied, but I think maybe I'm missing something, that it was easy in the sense that you have this. Maybe you can put this. Okay, this condition is.
So which one is it?
I think it's go back. Once.
And one
The
more.
fourth one,
Yeah.
exactly. So here, I mean, similar to what you said, but if, I mean, since the ij's in that case are in C0, so you have a coordinate so that they are smaller than epsilon over 2 from this coordinate on, okay? And then you can fix simply this y equal to x until this coordinate.
Yes. Yes.
And then this means that until this coordinate, you only have the norm of the
Yes.
ij's,
Yes.
the absolute values of the
Yes.
ij, which is less than 1.
Yes.
Okay?
So-
and from this coordinate on, you have zeros in
Yes.
the ij's, and then you only have
Yes.
the x
Yes.
and the yj, and then this is one is less than 1, and the other one is less than epsilon over 2.
Yes. So completely right. So in this concrete situation, this is the easiest proof
Okay.
one can do, but I wanted to use only the density. So if you only know the density, then you
Okay.
cannot be sure that
Okay.
the projection onto the first coordinates will be the one that you choose. And this is what makes this proof more complicated in the general case.
I see.
That you have to get rid of this, and this is why I have to do this averaging. But otherwise, of course, you get your y simply by projecting onto the first n coordinates, and that's it. Yes. And again, I really want to apply this in a more continuous version where you cannot exactly
Got it.
project, but you have a horizon cutoff function or something like that.
Yeah. Right. Okay, thank you.
Thank you. Okay, it has been a pleasure to listen to you talk, and it has come to me with memories many years ago, maybe 15 years ago. I was working with this code in spaces of weighted holomorphic functions, and then we used this kind of sorts and this whole property. And we were trying to solve a problem which is known as the biduality problem on spaces, weighted spaces of holomorphic functions. And we, of course, we were not able to solve the problem. It's a problem that has been open for more than 50 years or 60 years. But we somehow the situation is quite similar.
Yeah.
I mean, the spaces of weighted holomorphic functions fulfill this little O condition and this big O condition somehow. And we were able to characterize the positive solution to the biduality problem just considering this situation of being the HP naught, the small space, weighted space, and somehow as an M ideal in the big one. And I don't know if you have had the chance of looking at this work you did, or if you have thought if you could maybe solve the biduality problem using these things.
So I've certainly not thought about the problem in its complete generality, but only for, let's say, radial weights or so. And they serve here as an illustration of situations with little o and capital O that indeed are studied, but I haven't tried to apply this mechanism to this general spaces you are describing. Maybe it's worth it.
Maybe sort of I mean, it's now just thinking of how to make things somehow. There are things that I would like to think of that. Okay, thank you very much. Very nice.
Okay, more questions or comments or whatever?
If I understood properly, Carlton proved that little lip zero is an M-ideal in its bidual.
Yes.
Yeah. And then you prove that it's in fact is a M-ideal in big capital, I mean in big lip zero.
Under the density condition.
Under the density condition. And those two spaces are isomorphic. Yeah. I mean, so I deduce that not, I mean, the existence of an isomorphy does not allow to say that if you have an M embedding, you have another one. No? I mean, even if they are isomorphic.
It's strictly isometric.
Yeah.
So the isomorphism will destroy the norm.
Oh yeah, this is an isometry. Yeah. This is between the bidual of little lip zero and capital lip zero. You have a linear isometry. No.
Yes,
linear.
you under certain conditions.
Yeah, of course.
Mhm.
But this is a linear isometry.
Yes.
Okay.
Yes. Mhm.
Thank you.
Okay, well, what Nigel proved in this way is little lip zero is always an M-ideal in its own bidual,
Yeah.
whatever that might be.
Oh yeah, okay. Thank you.
What I do not know is if, say, beyond the density condition, beyond compact sets, is the little lip space always an M-ideal in the capital lip space. I do not know whether this is true in complete generality.
Yeah. Okay. Thank you.
Okay, more questions? No? So we thank the
Yo también estoy